Hey everybody, Dr. A here, and in this video we're going to be exploring another example of vector rectangular components. So let's go ahead and get started. In the given information, we're being told that if the resultant of the two forces acts along the negative y-axis and has a magnitude of 20 kilonewtons, compute the magnitude of F1 and its orientation, theta 1, which is in quadrant 4. Okay, so let's look at the diagram we're given. We have this set of Cartesian axes, and we have this known F2 that's coming down here in quadrant 3, and it's at a 60-degree angle measured from the negative x-axis. We have the unknown F1 coming down in quadrant 4 that's also at an unknown angle of theta 1. Now, we might seem like we're stuck here, but we also know that it's the resultant of this system is acting along the negative y-axis, and we know its magnitude is 20 kilonewtons. So here's what we could do. We can sketch that resultant down here, okay? We can say it's got that 20 kilonewton magnitude. So that is something we actually do know, all right? So when we talk about vector rectangular components, how do we tackle a problem like this? We saw a problem similar to this in one of our previous videos using a force parallelogram, but now we want to use vector rectangular components instead. Well, we follow the same process that we have been using in our previous examples of vector rectangular components. We first ask ourselves, should we use scalar notation or Cartesian vector notation? And remember, the answer to that is you could use either one, but for 2D vector analysis, scalar notation is usually more convenient and better compared to Cartesian vector analysis. Cartesian vectors are better used when we have three-dimensional vectors, which we have not gotten to yet, okay? So for this example, let's use scalar notation, all right? So I'm going to write solution. I'm going to say, let's use scalar notation for this, okay? Now, how do we go about using scalar notation on this diagram? Well, we go about it the same way we have before. Just because we have some different knowns and unknowns does not mean we have to go about a completely different process. We follow the same process we're familiar with. So we're going to say FRX is equal to the sum of the x components, okay? Now, here's the thing. Do we know FRX? Do we know something about FRX at this point? Yeah, absolutely. The problem said the resultant of the two forces acts along the negative y-axis, and we drew it here in red. So what do we know about FRX? Well, we know that the x component of the resultant, FRX, is what? It's just 0, okay? And then what we do is we write the sum of these two x components, knowing that we don't know F1 right now. So how do I write that? Well, I start with F1 times cosine of theta 1. Isn't that just F1x? Sure. This is F1x that we do not know currently, all right? And then what do I write? I say minus 15 kilonewtons times cosine of 60 degrees. So I have this handy little equation right here, all right? With the unknowns being F1 and theta 1. Now I do something similar with FRY. I'm going to say FRY is equal to the sum of the y components. And what does that equal? Do I know something about that? Yeah, absolutely. I know it equals negative 20. Where is the negative coming from? Well, it's pointed along the negative y-axis. So I can go ahead and say that's equal to negative 20 kilonewtons. And I go ahead and I write out the summation of those y components. Starting with F1, I'm going to say negative F1 times the sine of theta 1, and then minus 15 kilonewtons times the sine of 60 degrees. So now I have this second handy little equation. So what do I have here? I actually have a system of two equations here. And how many unknowns do I have? I've got two unknowns. Those are F1 and theta 1, okay? So I'm going to go ahead and label these equations. I'm going to call this first equation, equation 1. I'm going to call the second equation, equation 2, all right? And then I'm going to say from equation 1, I'm going to take this equation 1, and I'm going to do a little bit of rearranging here. I'm going to say from equation 1, F1 is going to be equal to 7.5 kilonewtons divided by cosine theta 1. So why don't you pause the video and do a little bit of algebra, rearrange equation 1, and make sure you get this same expression, 7.5 kilonewtons divided by cosine theta 1, okay? Now unpause the video. We're going to say now from equation 2, we're going to substitute this expression for F1 into this F1 term in equation 2. So the 7.5 kilonewtons divided by cosine theta 1 is going to get subbed in for this F1 term in equation 2. So if I write that out, what is that going to look like? Well, it's going to be negative, open parentheses, 7.5 kilonewtons divided by cosine theta 1 times the sine of theta 1. Where's that sine of theta 1 coming from? Well, that sine of theta 1 is this sine of theta 1. And then the second term is the same, minus 15 kilonewtons times sine of 60 degrees. And guess what all that equals? That equals negative 20 kilonewtons. So all I did was I subbed in this expression for F1 here, and I just rewrote this equation 2. And this is what I have in orange now. So what have I gotten myself set up for? Well, now I have this version of equation 2 only has one of those unknowns, theta 1. So I can rewrite equation 2, and guess what I can rewrite it as? I can say that's 7.5 kilonewtons times the tangent of theta 1 equals 7.01 kilonewtons. So what I did was I combined these constants, this negative 20, and I moved the 15 times sine of 60 over. So I collected all the constants on the right side of the equation. And then I also recognize that I've got a sine of theta 1 over a cosine of theta 1. So I rewrote that as tangent of theta 1. So I can do some basic trigonometry here and solve for theta 1. I use an arctangent operation. And I'll get theta 1 equals 43.07 degrees. And that's part of my answer. You could round that to 43.1 degrees if you want 3 sig figs. Okay? Am I done? No, but almost. Now I can substitute that theta 1 back into my rearranged version of equation 1, and I can solve for F1. Okay? So now I can say solve for F1 as F1 comes out to be 10.27 kilonewtons, and you could round that to 10.3 kilonewtons if you want 3 sig figs. And that is the conclusion of this example. So if you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.